Welcome to our next lecture in the series on condensed matter theory. In this video I want to give you an overview of the relativistic effects that we have in solids, especially focusing on spin-orbit coupling. And I will use a PowerPoint presentation in this video. All derivations that we need and that we'll encounter have been made in one of the previous videos, where I also go into the details of those derivations. And here I will just put everything together and present you what the effects in a solid are. So if we look at the spin, then this is a relativistic effect that we have in our equations. And let me just start with a very brief introduction on where quantum mechanics actually comes from, to see and get a feeling how Dirac came to the idea to include spin into his calculations, and give you the Dirac equation, and then we'll go from there and see how this changes the states that we have in a solid. So in the end, what we need to do is to solve the Dirac equation in a solid, which could become extremely complicated if you really want to do this exactly. Luckily, we do not really need to solve the Dirac equations. The rest mass of an electron is much larger than the energy scales of interest, such that we can use perturbation theory. And for that, we will have to derive a low energy effective Hamiltonian, and that's what we'll do in the first steps. And in this PowerPoint, I have some formula, but all the derivations have been done in previous videos, where we wrote down everything such that you can follow it. So here I'll just keep everything to a minimum and focus on what actually are the effects that we have in a solid. Let me start by a brief history, such that it becomes a closed, complete presentation that you can look at without the need to know all the derivations, and of course you have them. So quantum mechanics starts by the observations that people have in the optical spectra of atoms, where you nicely see these discrete set of lines, and you want to explain why energies are not possible with all, or these transitions are not possible with any energy, but only with discrete sets of energies, or that the electrons are only allowed to rotate in specific orbitals, the Bohr orbitals at that point in time. And there are all kind of relations between these sets of lines found during the 1800s, which then resulted in Schrodinger deriving his equations. So for hydrogen we have these beautiful series, and there actually is some systematics in these series. You'll find several spectral lines that are sharp, several spectral lines that are diffuse. Zeeman studied these lines as a function of magnetic fields. Some of those lines split in a magnetic field, some of those don't. You have singlets, doublets, triplets, and that's also related to sharp and diffuse lines that we have. So you can actually explain which lines are sharp and which lines are diffuse. If you take an alkali metal, sodium in this case, and you heat it up, then this electron from the S shell is excited into the P shell, the 3s to the 3p, and then it can decay. It can either decay into an S shell, giving results to sharp lines, that's where the S stands for, or it can give rise to diffuse lines when it decays back into a D shell, where diffuse stands for. And we now understand where this comes from, and it has to do with the angular momentum and the spin and the spin-orbit coupling that we have, where the sharp lines are really single states, and the diffuse lines, when you zoom in, are actually given by more than one line. Later found that you actually make the excitation from S into the P shell, which then was the principal shell. And even later people found that there is an additional shell, the F shell, which they called the fundamental shell. But there's really nothing fundamental about F, other than it sounds better than we found yet another set of spectral lines. You'd better say we found the fundamental spectral lines. So we have these different series, the Lyman series, the Balmer series, the Paschen series, with all these beautiful integer relations between the different excitation energies. And that gives then rise to the Bohr model and the Rydberg formula, telling you what these integer excitation energies are. Then Schrodinger came along and he said, well, instead of the need to talk about these integers, we can actually replace this by a single differential equation, and then these integer numbers immediately show as the normalization conditions. As long as you require that your wave function is normalizable, you will find an integer set of solutions related to the integer numbers of strings you can put, or waves you can put on a closed string, for example. And that's the Schrodinger equation. It has a kinetic energy, it has a potential energy, and then it has the Coulomb energy between them. And it acts on a wave function, so where classically the microstate is described by the position and momenta of all electrons, now the microstate is represented by the wave function. There are actually some problems with this equation. And first of all, it doesn't describe spin. It was very well known that you have the Zeeman effect. So some levels decay from a p to an s shell, for example. In a magnetic field, that line splits into two different lines. If you want to explain the periodic table, you say, well, each quantum state can be filled with a single electron, but then you have to actually double these number of states. The S shell can be filled not by one but by two electrons. If helium 1s1, hydrogen 1s1, helium 1s2. And the same is true when you look at the Stern-Gerlach experiment, for example. Also there you see this multiplicity of your states, where a single electron actually, or a single state in the Schrodinger equation actually can be filled with two electrons, which we call spin up and spin down. And then of course the equation is not Lorentz invariant. It's really the non-relativistic limit that we have. So Dirac hoped that when you correct the Lorentz invariance of your equation, if you make it fully relativistic, maybe you'll also find a way to include the spin multiplicity back into your equations. So how can we introduce the Dirac equation? Well, classically we know that E is a half mv square, or if we work in momentum, E is a 1 over 2m p squared. And in order to get to the Schrodinger equation, we replace the energy by an operator which is the time derivative, we replace the momentum by an operator which is the spatial derivative, and we let everything act on a wave function representing the microstate of your system. Relativistic, we have E is mc squared for a particle at rest, or E squared is m squared c to the fourth plus mc squared over mp squared for a particle with momentum. And we can now make the same substitutions where we replace the energy by a time derivative operator, the momentum by spatial derivatives, and have everything act on a wave function. And then we get the Klein-Gordon equation. Now, the problem with the Klein-Gordon equation is that it still does not include spin. Spin still has to be added in an ad hoc manner. And at the same time, it allows negative energy solutions. Actually, if you just look at E squared is m squared c to the fourth plus c squared p squared, then you already find there that the energy can be both negative or positive, and it's still a solution of this equation. Dirac didn't like the negative energy solutions, and Dirac didn't like the effect that there is no spin interaction, and he hoped to be able to correct both at the same time. And the reason that you can have negative energies is because the equation is on E squared and not on E itself. So Dirac had a look if you can find an equation that is linear in the energy instead of quadratic in the energy. So for that he said the energy must be equal to something in the momentum plus a constant. And he put in alpha I times the momentum plus alpha 4 mc squared, and then you want to solve this equation such that E squared is equal to P squared C squared plus M squared C to the fourth. And now the question is, what are the values of alpha I that we need to fulfill this equation? And you can write out these equations, and when alpha I alpha j plus alpha j alpha I is 2 delta ij, then you will find that energy linear in P plus mc squared, when you square it, will give you exactly P squared C squared plus M squared C to the fourth. The cross terms alpha I alpha j have to disappear for this to hold. Now, if alpha I would be a complex number, this is definitely not possible. But maybe these are matrices. If alpha I is a 2 by 2 matrix and your wave function is a vector with 2 components, then one component can be spin up, one component can be spin down, and you immediately have spin on a very fundamental level included into your equation. So we're looking for a wave function where the time derivative of your, or we're looking for a wave equation where the time derivative of your wave function is now given by something linear, and we're looking for these alphas i's, and maybe they are 2 by 2 matrices, and your wave function then is a vector of length 2. So your wave function has a spin down and a spin up component, and alpha I has 4 components. Then we require that alpha I alpha j plus alpha j alpha I is 2 delta ij. Well, the matrices that fulfill this equation are the Pauli matrices, but there are only 3 of them. And you cannot make a fourth one because you have only 4 components, and the Pauli matrices plus the identity matrix form a complete set. So there are only 3 2 by 2 matrices with which you can fulfill this. So with 2 by 2 matrices, nice idea, but you still can't do it. You have to go to 4 by 4 matrices to make this work. And that's exactly what Dirac did. So the wave function becomes a vector with 4 components, and our alpha matrices are now 4 by 4 matrices. Alpha 1, 2, and 3 are directly related to the Pauli matrices, and alpha 4 is just 1, 1, minus 1, minus 1 on the diagonal. And with this, we have our Dirac equation. We now find that there are 4 related particles. If you look at a particle with 0 momentum, then we have an electron with spin up, we have an electron with spin down, we have the positron with spin up, and we have the positron with spin down. And if you look at finite momentum, then depending if your momentum is parallel or perpendicular to the spin, you'll find a mixture between the large and the small component for your electron wave function with spin up and spin down, where we have the large component. In this case, I didn't normalize my wave function, which is much larger than the small component because energies are small compared to mc squared. And we can also look at the wave function for the momentum perpendicular to the spin. And again, we have a large and a small component. If you now look at the prefactors for the large and the small component of your wave vector, then you find as a function of kinetic energy, E minus mc squared, for a particle without an external potential, that the large component indeed is large and the small component is much smaller, and we here go up to energies of half an MeV in kinetic energy. So you truly go too deep into the relativistic regime. Instead of just looking at the prefactors, you can look at the prefactor square so that you can nicely see that the sum of the two is always 1. Now, the energy scale of interest for solids is in the electron volt scale. So here I show you, instead of going up to half a mega electron volt, the small and large component when you go up to 100 electron volt. And on this scale you basically see no change. One is 1, the other is 0. If we look at 1 minus the large component and the small component, then of course both are equal. And we can now plot this as a function of the kinetic energy, and you nicely see that in the range from 0 to 100 electron volt, this basically gives you a linear dependence, a first order correction with a prefactor of 0.0001. So the small component is really small. 0.1 per mile if you stay with energies below 100 electron volt. So that is something that we can use, and we can then say, well, let's have a look at perturbative expansions. Of course, we also need to think what are the relevant kinetic energies in a solid. Are they really this small, or how big do they actually get, to see how far we have to go into such kind of perturbative expansions. So let's first have a look at the kinetic energies that we have in a solid. And for that we can use a free electron model. We've seen that there are several materials, the alkali materials for example, where a free electron model works good enough. So let's have a look what happens when we make this free electron approximation. The energy momentum dispersion is just p squared over 2m. At the zone boundary you get of course folding, and this should work for the alkali metals. So let's have a look there. So at the zone boundary your bands fold, and then of course the periodic potential makes opening of small gaps, but that's not so important for the case at the moment. Now the Brillouin zone is not simple cubic, but body-centered cubic, such that our Brillouin zone looks like the shape you see here. If we move in momentum along the diagonal, we go from gamma to P, then to the next Brillouin zone, enter in H, and then the next Brillouin zone we come back to P and gamma again. And here you show in red the density functional theory bands of lithium, and in blue the free electron dispersion, p squared over 2m, in terms of electron volts in an extended zone scheme. So the bands are reasonably free electron-like, especially when you go from lithium to sodium to potassium, rubidium, cesium, francium, just going down into the periodic table. What happens is that the atoms get bigger and bigger, therefore your unit cell gets bigger and bigger, the reciprocal unit cell gets smaller and smaller, and the horizontal scale is the same in absolute units for all elements that we show here, making the Brillouin zone smaller and smaller. So if we now want to have a look at the velocity of the electrons, then that's the largest at the Fermi energy, which sits roughly somewhere here in a one-dimensional lattice. It would be at a half of a Brillouin zone. Here it's a bit different, but you have the same number of electrons per unit cell, and it's just that the reciprocal unit cell is getting smaller and smaller. So if you just look at the element, the real space lattice vectors, then you calculate the reciprocal unit cells, and with that the Fermi energy is determined. Then the Fermi energy is getting smaller when you go from lithium down to francium, and with that the velocity in terms of the speed of light is getting smaller when you go from lithium to francium, and with that the small component of the wave function is getting smaller, or the relativistic energy correction that you have is getting smaller when you go from lithium to francium, which is somewhere of the order of 35 micro eV for a free electron model of lithium to something like 7 micro eV for a free electron model of francium. So all nice and well, something is missing here, because if this would be the relativistic corrections that we have in these kind of solids, then these are much smaller than temperature and therefore would be completely neglectable. You might also have known that the heavier the atom, the more important the relativistic correction should be. So just the kinetic energy of the valence electrons is not what is giving you the relativistic effects in a solid. So what is missing? And if we just look at a solid, then of course for the bonding and the valence electrons the free electron model works, and this is roughly what your kinetic energy indeed is, but this is not the complete story. We have a crystal lattice, we have charged nuclei, and at the nucleus the potential is actually diverging. So in between two atoms you have a constant potential, and there you can use these free kinetic energy models. Close to the nucleus, where there is of course no chemical bonding, your potential diverges. So if you just make a very simple model, let's say the electron is traveling, and when it gets close to the nucleus it's accelerating, and then further away of the nucleus it's deaccelerating again, then you can calculate what the kinetic energy would be, and with that what the large and small component would be, or the correction that we have. And then you find that the larger the kinetic energy, the larger the correction would be, such that in the interstitial region, indeed your small component is of the order of 10 to the minus 4, giving rise to extremely small corrections. But close to the nuclei, the small component actually gets very large because your potential is divergent. So we have to look a bit closer at what is really happening close to the nucleus in order to see what the relativistic effects are in our solid, because that's where the relativistic effects happen. In the interstitial region you can get away with neglecting all relativistic effects. It's micro electron volt, but close to the nucleus, there the interactions can become much larger. Now the nice thing is that close to the nucleus your potentials are spherical. So we can either say we have a spherical potential, everything is atomic-like, and we have relativistic effects, or we say we are in the interstitial region, you have bonding, you have all your chemistry and physics playing, but there are no relativistic effects that we have to treat explicitly. So do we need to solve the full Dirac equation for the entire solid? No, we can treat these interactions perturbatively close to the nucleus. Let's see where we stand. Spinorbit coupling is a relativistic effect. Electrons in solids only have large velocities close to the nucleus. Close meaning half a Bohr radius, a quarter of an angstrom. At that distance everything is spherical, you don't have to worry about chemical bonding. Your wave functions are just given by orthogonalizing to the core nuclear wave functions. They're always the same, atom dependent, completely independent of all chemistry that we have. So this is only valid close to the nucleus, not in the intermediate range. Of course, there you have all your bonding and your chemistry and physics playing a role. So a reasonable approximation is to make a tight binding Hamiltonian, where we have a local atomic-like basis. We include the spin-orbit coupling as if they are the atomic coupling constants, because close to the atom you have, or close to the nucleus you have these atomic-like wave functions. And then put in the interactions and the hoppings between them. So let's see how this works if you go back to the alkali metals from lithium to francium. We have our atomic orbitals and atomic wave functions. Now the black dots are the nuclei of our different atoms. The blue line is the radial wave function, the atomic radial wave function. Now this wave function neither has a kink nor is zero at the next nuclear site. So that is something we have to solve. We make the Wannier functions out of them. Close to the nucleus, not much changes. There is some overall scaling maybe in here to make your wave function normalizable. And it's going to be zero at the nearest neighbor, such that you have all Gauss laws fulfilled. And there are no divergences anymore. And with those Wannier functions we can now build the tight binding Hamiltonian. The wave functions I show here are not completely the Wannier functions because I didn't orthonormalize them, but that doesn't matter that much. We can now make a tight binding description of these atoms. The plane wave at k is 0 is just a constant. Then at the zone boundary we have a single wave, and at the next zone center the wave function is doubled. That of course is folded back to gamma again. If you look at the charge density that you have, then well, you have of course these kinks close to the nucleus because it's a 2s wave function. but in the intermediate range you find that indeed your charge density is relatively constant. The same is true for the wave function at the x point, where you have reasonably sine-like dispersions. Of course you have this additional kink because we're talking about the 2s again. At the next state in the zone center, you should realize that you can't use an s orbital anymore, so the next one should be a p orbital. If you shift the phase of your wave function, that doesn't change the energy. Then we have the node at the atoms, and we can represent this by p wave functions. And also there you see that you get a reasonable approximation of this system. So if you move in the x direction, you have the px orbital, in the y direction the py, in the z direction the pz. It all fits nicely. You have 3 atomic p orbitals, you have 3 spatial directions. And you can make a tight binding Hamiltonian, including the s and the p orbitals, for your free electron bands. And that's exactly what we have here for lithium, where we have here now also our Bernier functions, or for sodium, potassium, rubidium, cesium, francium. Look at your wave functions. I changed the lattice constants, or the plots are such that the distances is all the same. Of course the lattice constant change, and you see that you get a nice representation in terms of a tight binding Hamiltonian. Now we can also calculate what the spin-orbit coupling constants should be. We have our large components of the wave functions and the small components. You see that in the interstitial region where the physics happens, so from somewhere from 1 to 3 Bohr radii, the small component actually is completely zero. So where the last lobe is where the chemistry and physics takes place, and that's where the small component is completely zero. But if we now zoom on into the first half Bohr radius, then you see that close to the nucleus you have a small component. And that's where the relativistic effects take place. So actually there is quite a nice separation between where relativistic effects play a role close to the nucleus and where chemistry plays a role in real space. And that allows you to make these simplifications. Now, with that, our full Dirac equation can be simplified, and it becomes this nice equation where we have our kinetic energy plus a correction to the kinetic energy, the mass correction term. We have the potential energy and a correction to the potential energy term, the Darwin term. Both of them are important for quantitative effects. Qualitatively, they do not change the physics. Then we have the Coulomb energy, and we have the spin-orbit interaction, which we can write as if we have a spherical potential, because it's only important close to the nucleus where your potential is spherical. And we basically have the atomic interactions close to the nucleus, and also only interactions between states with the same angular momenta around the nucleus. Angular momentum in a solid, in principle, is ill-defined, because, well, what is the center around which you rotate? But we're only interested in the angular momenta around the divergent potentials within half a Bohr radius around that divergence potential. And there is a clear center around which you can rotate, and therefore a clear definition of what an angular momentum operator is at that site around that nuclei. The spin-orbit interaction can in principle be related to a Lorentz force. An electron rotating in an electrical potential can of course also be seen as an electron that is stationary and the potential that is rotating. So then it's coming from a current, and a current would generate a magnetic field. So if we write down the angular momentum as r cross p, then put in the potential times r and 1 over mc squared times the momentum, then this is the velocity, that is the electrical field, and this is E cross V, and E cross V is the magnetic field, and this is just the interaction of the spin with the magnetic field that is generated because the electron sees the nuclei rotating around it. just a change of reference frame where the electron now sees an effective magnetic field. And this is the Lorentz force that you have due to that magnetic field. So that's the new term that we have in our Hamiltonian. As we have spherical symmetry locally, we can calculate this interaction by separating a wave function into a spherical and the angular terms. And this interaction is totally determined by the wave function close to the nucleus. And there we can separate the wave function in a wave function depending on r and a wave function on theta and phi, such that the interaction now separates into an interaction of the radial wave functions and the angular wave functions. And the angular wave functions actually we can solve analytically. And we have our spin-orbit coupling constant zeta times the angular interaction on the angular part. So that's the spin-orbit interaction. Note that I use here small letters for our operators, and once we go into many electron states, we like to use the small letters for operators acting on single electrons and the capital letters for interactions on many electrons, where the total angular momentum is the sum over all electrons and their angular momenta, and the total spin is the sum over all spin. The spin-orbit coupling constant, or the spin-orbit interaction, acts on each electron separately and not on the total angular momentum times the total spin. The later is an approximation that has been used in the early days in atomic physics. If you look at the term energies, then their splitting looks as if you split into capital L times capital S total angular momentum coupled with total spin. That is, if your local angular momentum coupling and local spin coupling by Hund's rule exchange and Coulomb interaction is stronger than spin-orbit coupling, which is basically true in the entire periodic table. You get an effective low energy operator that looks like this, but really this one, each electron separately, is the one that is more accurate. Now you can make an approximation where you can replace this operator acting on each electron separately as an operator coupling the total angular momentum with the total spin. The later is an approximation. Actually, as we have now computers that can easily handle all these atomic multiplets, it doesn't make things even simpler, because this is a many electron interaction, whereas the first one is a single electron interaction. So at the moment there is really no need anymore to make this approximation. Most of all because it's just not completely valid. Yes, you can describe certain effects, and once you have those, we can talk about them. We'll do this when we do many electron magnetism. But it's just not accurate. It's going to miss all kind of von Vleck interactions. And your equations are harder to solve. So there's really no need to make that approximation. Now let's have a look what the size of our spin-orbit coupling constant is. And we can calculate those for the atoms, and because everything is derived or everything is close to the nucleus, it's going to be valid independent of the chemical environment. So if we look at the 3D series going from scandium to zinc, you're somewhere from 10 to 100 milli-electron volt, whereas when you're in the 5D series, 3, 4, in the 6D series, you're a quarter to 1.3 electron volt. So we're in the range of a few milli-electron volts to up to an electron volt. If you look at the 4 and the 5F series, you see that, well, somewhere between 36 to 300 milli-electron volt, 93 to 670 milli-electron volt. So that's not a huge energy scale, but of course compared to temperature it's definitely sizable. So you will be able to notice these effects. If you look just at the Hartree-Fock values, going through the periodic table, just having a look at the last elements that you fill, so the 2p for bore to neon, then you see that you start somewhere at 10 milli-electron volt and you go up to somewhere about half an electron volt here in the 5D series. I had the 6D series here in 3, 4, 5. Yes, I had the 6D series in here as well. So then it becomes slightly larger still. So somewhere between a milli-electron volt and an electron volt is where your coupling constant sits. These are the Hartree-Fock values, and they pretty much well agree with what the experiment tells you. Now, you can make an approximation to estimate what your spin-orbit coupling constant should be. And again, this has also largely an historical background, where people just looked at the coupling constant that you would find for a hydrogen atom with an effective charge. So we assume that our potential is Ze divided by 4 pi r. Our radial wave function is the radial wave function that you find for a hydrogen atom. And then we can just calculate the effective coupling constant between two hydrogen-like wave functions. And you'll find a beautiful constant, and it scales with Z to the power 4 divided by n cubed, and then L plus 1 to L plus 1. So it scales with Z to the power 4, it scales with 1 over n to the power 3, it scales with 1 over L to the power 3. So the heavier your atom, the larger Z, the more important spin-orbit coupling becomes. But then, of course, you also get a larger principal quantum number. So the smaller your spin-orbit coupling becomes. And then when you do not fill a p shell, but a d or an f shell, also there your spin-orbit coupling constant is reduced again. If you now plot here in blue the Hartree-Fock values and in red the hydrogen effective atom values, you see that you do get indeed these jumps when you go to a different subshell, but the hydrogen values are somewhere between a factor of 10 to 100 larger than what you find in the Hartree-Fock values. And that has to do with the additional charge of the electrons that screen your local charge. And that screening is smaller for the beginning of a subshell than it is for the end of the subshell. So you get this kind of behaviors where the effect inside the subshell actually scales stronger than Z to the power 4. But you do get, well, what it does get right is these different jumps in there. One has to be a bit careful because, well, in the early days, just doing a mean field calculation with enough accuracy to actually get those blue dots was difficult. So in the older literature and textbooks, you will often find the red dots where you start from a hydrogen atom as an approximation for the spin-orbit coupling constant. But again, there's currently no real need to do this, as calculating these atoms is seconds on a computer, so there's really no need to make those approximations anymore. Very good. Especially Landau and Lifshitz make the former approximation, and they popularized this a lot. It's an extremely good textbook. They do extremely many things right. But this is an approximation that we no longer need to make. And you should be a bit careful because, well, you do get some different results in there. Now, given all this, how do we include this into our tight binding Hamiltonian? And we have seen before examples where we made a tight binding Hamiltonian, and for that we neglected spin. What we can do now is double your basis set. When you think of an s orbital, you now have an s orbital with spin up and you have an s orbital with spin down. The s orbital with spin up can hop to an s orbital with spin up at a different site, making a tight binding Hamiltonian for spin up. The s electron with spin down can hop to an s electron with spin down on a different site, making a tight binding Hamiltonian for spin down. These two Hamiltonians are just exact copies of each other. They are completely equal. One's acting on the spin up states, one's acting on the spin down states. And then on top of that you put on the spin orbit coupling interaction. And of course for s electrons there is none, but where you have p electrons there is a spin orbit coupling interaction between p electrons, or for d electrons there is an interaction between the d electrons. The coupling interaction L dot S between p electrons can be written down quite easily on a basis of the complex spherical harmonics. If we have an angular momentum -1, 0 or 1 and a basis of spin down, spin up, spin down, spin up, spin down, spin up, then you see that for the p shell we now have 6 basis states. On the diagonal it's just Lz times Sz, so -1/2 for the spin down times -1 is 1/2. -1 angular momentum down times the Sz of 1/2 gives you -1/2. When Lz is 0, the diagonal is 0. Lz is 1 times spin -1/2 or spin +1/2 is giving you the states on the diagonal. And then we have the L plus S minus L minus S plus operators, which gives you these off-diagonal terms, coupling states with P0 spin up with P1 spin down, or the other way around, and the same here between -1 and 0, the ladder operators that we have between them. So our tight binding Hamiltonians we normally did not write on a basis set of the complex spherical harmonics. They're much nicer to look at on the basis of the real cubic harmonics. So we can of course make a basis transformation where you linear combine the Lz is -1 with the Lz is 1 state to a px and a py orbital. And if you make that combination then on the basis of the cubic harmonics, the px, the py and the pz, again with spin up and spin down, you have your spin-orbit coupling Hamiltonian. So you now have your tight binding Hamiltonian for spin up and spin down, for p electrons both as 6x6 matrices, block diagonal in spin, and then for each side you have locally your spin-orbit coupling Hamiltonian that you add to this. And together you have to diagonalize now a 6x6 matrix for each K point. So that's how you can add spin-orbit coupling to your tight binding Hamiltonian. So with that, we come to the end. I hope to have shown you how we can add spin-orbit coupling to a tight binding Hamiltonian, that the spin-orbit coupling is something that lives locally, that there are additional relativistic corrections relating to the mass, velocity and Darwin term. But in terms of your tight binding Hamiltonian, they just slightly change things like on-site energy as a sigma, pp sigma, your hopping matrix elements. Well, we took them from models, or we take them from density functional theory. That these values change by a few percent doesn't really matter all that much for the physics that comes out. Spin-orbit coupling, of course, because it couples now the spin into your states, makes a qualitative difference, and that's the important relativistic correction that we have. We'll come back to different models where we have spin-orbit coupling, either when we discuss topological states and topological surface states, where you have to include spin-orbit coupling to be able to describe real materials. So there we truly make an example of an s and a p orbital on a cubic lattice, and see how spin-orbit coupling then changes your band structure. And in later lecture, when we discuss magnetism, because the magnetism has all to do with spin and the spin arrangement that we have of the local electrons, and then the coupling of the spin direction to the lattice direction is actually given by spin-orbit coupling, and that's where your magnetic anisotropies come from. For now, thank you very much for your attention. We see each other later. Stay healthy.